Hey, this is OrgoChemSimplified, and our goal is to make organic chemistry simpler. And we're going to do so by developing a framework for tackling these mechanism problems with confidence. And today we're going to learn about radical mechanisms in the process. So here we have a radical problem, and the first step in the framework is to identify the reactive groups in our starting materials and figure out how they react. Right? So we have two starting materials. We have this alkene here, and we have NBS, or N-bromosuccinimide. And NBS looks like this. 5-membered ring with a nitrogen, and this is bonded to a Br. So first thing we want to ask ourselves is, when we identify our reactive groups, is which one is more reactive? Well, this bond is especially weak. So because this bond is especially weak, it's probably the first one to react. Also, we know that this H nu, all that means is we're using electromagnetic radiation. And that's going to put energy into the system and probably break the weakest bond. And as we know, this is the weakest bond, right? The second step in the framework is to actually perform the first step, the one that's the most likely. And we said this N-Br bond is especially weak. So we put in light energy or electromagnetic radiation. It's going to break this bond, and we're going to form radicals. Okay? So when we do that, we form this radical and a Br dot radical. Well, I want to focus on this radical first because this is what's actually going to react with our alkene. Okay. And so the third step is to continue with the logical progression towards the product by repeating steps 1 and 2. Right? So step 1, identify the reactive groups in the materials and how they react. Okay, so we have a radical here. And what do radicals like to do? Radicals either add to the pi addition, they add to a pi cloud, so they would add to this double bond, or they would abstract a hydrogen. And when faced with those two choices, the most likely choice is hydrogen abstraction. So now we have another question here, which is it going to abstract this hydrogen, or is it going to abstract this hydrogen on the end? Well, the way we can answer that is through stability of our intermediates. So the fourth step is use either the products or the intermediates as a guide when we get stuck, right? So let's abstract this hydrogen and see what intermediate we get. So these fishhook arrows mean that only one electron is transferred. And this electron is placed back onto the alkene, right? So this forms an NH bond, and the structure we're going to focus on now has the radical on the alkene, right? So if we abstracted this hydrogen, right, we would get a radical here instead. But that wouldn't show resonance. However, this compound does show resonance. Why? Because we can break this alkene double bond and place this radical here. So this shows a resonance arrow. So this is another structure we could have, right? Okay. So as we can see, if we abstracted this hydrogen as opposed to this hydrogen, we would get resonance. So both these resonance forms can react. Right? And what are they going to react with? Well, what do we have left over? We have this bromide radical left over. So remember that Br dot, it's going to come back. So these combine to form two products. The first product is this. We've just formed a bond to the Br where the radical was. And the same thing for this compound here. Okay, so that's the end of the mechanism. And step 5, let's continue to the product. So now that we've completed the mechanism, we have to answer the second question, which is which is the major product of these two, right? And the way we want to do that is we want to look at the intermediates, figure out which one is the most stable, right? So is this intermediate the most stable, or is this intermediate the most stable? Well, what kind of radical is this? This is the secondary radical, right? So similar to hyperconjugation in cations, as we've seen in the alkene chapter, radicals also undergo hyperconjugation to increase stability. So because we have two groups partially donating their electrons, as opposed to one group here, because this is primary and that's secondary, this intermediate is going to be more stable than this intermediate, right? So that means we're going to get more of this intermediate than that intermediate. And if we have more of this intermediate, we're going to have more of this compound, right? So the major product is actually going to be this compound here, because it is a secondary radical as an intermediate. So as you can see, if you develop a framework for attacking these types of problems, there's a lot less you have to worry about, and it becomes much more methodical. And so I want to repeat the framework for you very quickly. The first step is to identify the reactive groups in your starting materials and figure out how they react. The second step is to perform the step that is the most likely. The third step is to continue with the logical progression towards product, repeating steps 1 and 2. The fourth step is if you get stuck, you want to use your products or your intermediates as a guide. And the fifth step is just to continue towards the product and reach it. That's what we want here. So if you like the video, if you like the videos that we have here, please subscribe and please give us a thumbs up. And if you have any questions or comments, please leave them below. And this channel is for you, so I would encourage you to participate and to help us contribute to the community by leaving comments or questions so I can get back to you, and hopefully we can make some other videos of problems you would like to do. But thanks for watching, and I'll see you next time.